Um, yeah, I will get started. Good morning, everyone. I'd like to thank the organizers for allowing somehow more of an operational thinker like myself to be speaking to a room full of resource theorists such as yourself, and also to Julia for really setting the stage for the things that I will talk to you about for the next 20 minutes or so. But before I get started, I'd just like to briefly introduce myself. So I'm a Maltese physicist from Malta. This is Malta. This is actually a summer school on quantum thermodynamics that we organized a year ago, which happened here, or a year and a half ago, and it will happen again this September. We will have streams on thermodynamic uncertainty relations, quantum error correction, clocks, metrology. So I urge you to keep an eye out. Maybe PhD students of yours or postdocs or yourself would like to attend. And I am a PhD student in the Quid Physics group in Vienna, working loosely on quantum thermodynamics and quantum information. The motivation for this talk, and you're seeing this quote perhaps in full after Philippe already flashed it, is this quote by Landauer, that information is not an abstract entity, it's physical, and this ties it to the physical restrictions of the physical world, right? Like the thermodynamic restrictions. And so what we want to think about for the next 20 minutes is how does thermodynamics restrict our ability to process quantum information? And Julia has already pointed us in this direction, saying that somehow the irreversibility that we introduce is going to determine our ability to perform a task accurately. Now, the way I think about irreversibility is perhaps not in this style a la Pet's recovery, but in this style a la Crookes, in fact. And so we're going to meet the entropy production. Okay, so entropy production, for those who are not acquainted with it, is a quantifier of somehow the dissipation or the irreversibility of a quantum process. So if we have something like this, we have some sort of agent who's going to do a unitary across a system and the reservoir, and we see the state of the system and the state of the reservoir after. This entropy production somehow quantifies how much the reservoir has changed, perhaps because of this dissipation, and also because of correlations that can form here. And if we are going to do something which is resourceful, it means that, or what is something which is resourceful? Something which is resourceful is something which allows us to accomplish a task well. And we want to quantify this, so we're going to use the fidelity from the state we achieved to a target state to quantify how well we did something, and so how resourceful something we use is. Okay, good. So this is our setting. And the talk will be structured as follows. So first, I will talk to you about timekeeping as a resource and accurate quantum information processing, which was the subject of this paper. And then I will talk to you about some thermodynamic resources that pop up in the task of Schumacher compression. And in spirit, I would say that this is like, the same questions which motivated Julia, but really in an explicit context now. Really, let's see them manifest. So to begin with, what is a clock? Okay, so we want to talk about timekeeping. What's a clock? So a clock, in my view, has three parts. So first, let's think of this pendulum clock. Okay, so we're going to produce a frequency. Now, producing a frequency is something which is symmetric in time. So far, we're not able to keep track of time, but we have a frequency. And now there's going to be this escapement mechanism, which introduces some friction and somehow counts the beats of this pendulum. And then this is translated into the clock face, and you're able to read off the time. Okay. Now, what is very particular about this introduction of friction is that it is the introduction of this entropy which allows you to break this symmetry in time of the production of the frequency, and so allows you to keep track of time. And this relationship between entropy production and timekeeping was really pointed out in this work by Mark Mitchison, Paul Yerker, and others a couple of years back, that sort of these quantum clock models here that use the thermal machine framework to examine the physics of timekeeping. Here you see that if you use sort of this minimal model of a hot qubit and a cold qubit, they exchange some heat, and you allow the sort of overlap virtual energy splitting between these two qubits to be resonant with a ladder. So you exchange heat here, this is resonant, and you start moving up the ladder, you have a photon out, which is your tick. So what is the accuracy of such a clock? The accuracy of such a clock is how regular is the photon emission. If you're expecting a photon out at a time tau to keep track of these times, then if this starts to vary, then your clock is not so accurate. And this is what this term tells you, that the clock accuracy is the ratio between the expected tick time and how much that varies, okay? So, and maybe you ask, where is the frequency change here? The frequency change would be the shift in the populations of a virtual qubit subspace here. And the point of this work was to show that the clock accuracy in this specific model is bounded by the entropy produced per tick. So there is a relationship between timekeeping and thermodynamics. How does timekeeping enter in quantum information processing? So depending on where you see yourself on these three sections, a different picture will appeal to you, right? If you're a mathematician, then quantum computation is just, you think about the special unitary group on these projective Hilbert spaces and you're fine and happy. If you're a computer scientist, you think about architecting some string of gates such that you build a probability distribution which you can sample from that can solve BQP problems. But if you're a physicist, you want to generate a unitary by enacting a Hamiltonian for some amount of time. If you're an ion trapper, you have to fire a laser at an energy splitting, address that for a specific amount of time, because a different amount of time will give you a different unitary. How different? How much can this contribute to, let's say, the failure of a circuit? If I have a couple thousand gates I want to run, and each of them has some bad timekeeping, how much can this contribute? This was the question which motivated us in this work under here. And what we need now to be able to answer this question is, how do we model accurate timekeeping? Okay, so we already spoke about things like expected tick times. How does this vary? A tool here people introduced is this so-called tick distribution. So a perfect tick distribution for a single tick would be something like a Dirac delta. So let's say we want to do this time evolution and we want to know the statistics of doing this. Then if we can always do this perfectly, then it's kind of like you throw in a Dirac delta into this time evolution and you always get rho prime out. But if your clock is somehow a bit imperfect, so the clock accuracy is not perfect, and maybe you throw in a Gaussian and you get this instead. Now, maybe those of you that like playing around with things like this can already intuit that this is a mixed unitary channel. What does this mean? I sample from my tick distribution, I get some time out, and for a given time, I get a different unitary, which means that if I consider this distribution over all times, I'm going to get a different unitary each time. So it's a mixed unitary channel, and in particular, it's a dephasing channel. So if we look at this in the energy eigenbasis, what we find is that this tick variance here is creating a dephasing envelope in the energy eigenbasis of the Hamiltonian, which generates this computation, okay? So this is what we expect, this time evolution, but instead now we have dephasing in the energy eigenbasis. And so now our tool to examine how imperfect timekeeping is going to impact the computation is indeed a dephasing map. And maps, they're nice and we can work with them. In particular, there is something called the average gate fidelity, which allows you to quantify how much a noisy channel is degrading an operation you would like to do. In particular, maybe you do this over the Haar measure, so you consider this over all inputs. And this is what we did in this paper, and we proved this nice bound. So the average gate fidelity over a circuit with L C-naughts in total over n qubits is bounded like this. And I don't know, if we break it down a bit, the nice thing here, so if the fidelity is 1, you want 2n plus 1 over 2n plus 1, that's 1, so very good. But now we have this factor here, which is going to make this go down, and it's exponentially impacted, inverse exponentially rather, by the clock accuracy. Okay, so dependent on what the clock accuracy is, your achievable average gate fidelity is going to be limited by this clock accuracy. How do you prove this? Well, you assume that, well, first of all, let's say we care only about non-local gates to make this problem somehow a bit tractable and interesting. So we're going to count how many C-naughts we have in a circuit, and we're going to count how many C-naughts we have in a given time step. We assume that each C-naught is timed in the same way by the same tick distribution. So in a given time step, I'm going to have two, let's say, independent dephasing channels here and here. And now the game is to determine for an arbitrary circuit that can have as many C-naughts as I like in as many different places as I like, how this thing is going to stack up and make a big channel whose average gate fidelity I then want to bound. The nice thing is that when local dephasing channels build, a dephasing channel is that, mostly you get the identity, but sometimes, you get a sigma z or some sort of Pauli hitting you away. But these clocks, if they're reasonable, they're mostly going to be this identity. So this indeed allows one to make use of something called the unitarity, which for non-destructive channels bounds the average gate fidelity. Why should you care about this? Maybe for the mathematically inclined in the audience, the average gate fidelity is a 1 norm, the unitarity is a 2 norm. We're dealing with Pauli's as Krauss operators, so in the 2 norm, they go away. And that's how you derive this. Very good. So you might think, I said, I want to bound the fidelity by some quantity, and then I want to relate this to the entropy production. Really great, I inherit this prior work from Pauli Yerker and others relating the entropy production to the clock accuracy, and I can directly throw this bound in here, but indeed this is an open problem for people that want to work on this. A generic bound relating the accuracy of a clock to the entropy production per tick is not known in a model-independent context, so we can't do that directly. Okay, very good. So now we can switch gears. Now that we've understood that timekeeping limits our ability to do complex quantum operations, let's investigate quantum compression as a bit of a paradigmatic scenario. So it is the compression of quantum information, IID, quantum information, a la Schumacher. So you have some source, it's going to give you a pure state with some probability. There is some agent Alice, she samples from the source and builds a string of these pure states. She does a typical measurement. What is a typical measurement? A typical measurement allows you to determine whether a string that you've sampled is likely or not relative to the source you have. Why is this useful? Because if you look at these likely strings, they form a subspace. A subspace which, when you go to large M, is populated up to probability, which is up to unity, so it's really likely that you end up in this set. And so then what you do is you look at this possible set of strings that show up here, you look at this typical subspace, and you rotate the typical subspace onto the, let's say, the first k qubits, and then you throw away the rest. So that's what happens here. You check if it's typical. If it's typical, you rotate the typical subspace onto the first k qubits, and you can throw away the rest without damaging the fidelity too much. What happens, though, is that now you're encoded into a lower dimensional state, and what Bob has to do is append some zero states into here to be able to decode the message. When it's atypical, you send over a guess state, which might have lower fidelity than the compressed message. So this is what's happening here. Naively, where does the thermodynamics hide here? Well, in doing the measurement, in timing these unitaries, and am I missing something? Yes, in appending these zeros. Because zero states, like some people in the audience have thought about deeply, cooling to the ground state sometimes requires infinite cost, okay, a la Nernst. So is this reasonable that Bob can get as many of these as he likes? And so this is what we look at in this work that was on the archive around 2 weeks ago. So we allow our agents to have access to thermal states at some fixed temperature for free. Let's say they interact with some environment and they can get some thermal states here at some temperature. And Alice is going to use this thermal state as a probe, and we will investigate what this means shortly. And Bob is going to use these thermal states to append here, and we're going to see how much this impacts his fidelity. And we also have the impact of imperfect timekeeping. Okay, so this is like a, let's say, thermodynamically realistic quantum coding, if you like. So what is the von Neumann measurement scheme? So you might have learned, that measurement, you can write down a channel, right? So for some measurement outcome, I have these projectors. For another one, I have these projectors. And measuring is just enacting this channel. But if you want to be more physically minded about it, measurement is actually the process of entangling your state with some probe such that the correlations encode the measurement statistics. And this is what is known as the von Neumann measurement scheme. It leads to somehow Darwinism if you really take it to its conclusion. And it allows us to thermodynamically model the sort of the task of measurement. And that's what's done in this paper, where they examine what the state of the probe, how it affects your ability to do measurement. So what you're going to do is you're going to change the state of the probe, and you're going to see how it impacts your ability to do measurement. And in particular, you might imagine that if the probe were in the zero state, you get the expected perfect measurement statistics. But if it's thermal, I start to get statistical mixing. So I have some populations in some energy levels that I don't like. And basically, they will sometimes pull in this projector when I don't want it to. So this is kind of how this works, that the different populations, the thermality of the probe pulls in measurement statistics that I don't expect erroneously. And there is this quantifier, which they introduce in this paper, which is the maximum correlations you can form with the probe for a given temperature of a probe, for a given Hamiltonian, and for a given dimension. So if any of these three diverges, which is to say, if you have a zero temperature qubit, if you have a qubit with an infinite energy splitting, or if you have diverging dimension, you will be able to recover perfect measurement statistics. And so now we're going to investigate this in the typical measurement in quantum coding. So let's summarize maybe the results that I got in this work. So if you just consider the typical measurement first, and maybe for people not familiar with Schumacher compression, what you expect is this fidelity to be lower bounded by 1 minus 2 delta. Okay, this is like the generic result in quantum coding, that in general delta is related to how many samples you make, and delta converges to 0 as n goes to infinity. Okay, so this is how quantum coding works. But you see that the correlations you form with the probe start to mess with this because of the statistical mixing. So when I have some populations in the probe which are not in the ground state, they're going to pull in some erroneous statistics and mess up this communication that Alice is trying to do with Bob. Why? Because she's going to send over atypical sequences sometimes, thinking they're typical. So this is an issue. Next, when Bob tries to decode and he pulls in these thermal states are also going to introduce error into this model. Interestingly, in a way, which if the protocol is going well, so you're able to compress a lot, you have to add in more states from here. You have to add in more states to be able to decode, right? So if this is smaller, then the junk is bigger that I have to account for in decoding. And this means that it introduces more error the better I'm doing, right? So in fact, here there is this exponent which is related to how much I'm compressing. So this is the amount of qubits you throw away. So this effect of the thermality of the qubits you use to decode is exponential in the number of qubits that you use to decode. So there is this interesting effect here, which is the worst of them. And the imperfect timekeeping, I mean, again, you see dephasing twice. So these are more or less the insights from looking at coding in a thermodynamic way. But, maybe we're a bit, still have some energy. And we think, okay, so we got these thermal states, we got them for free, but maybe now we can use the thermal states to improve the states we have. And in doing so, improve our ability to do this protocol in a thermodynamically consistent way. So what do we do? What we do is we cool the states that we have access to. So if we have access to these states tau beta, we can line them up such that their energy splitting is going to increase. And we can swap populations with them such that our target qubit gets colder, colder, colder. And we can now use this as a resource for the probe, the measurement probe, and for the decoding qubits. And now this particular cooling protocol, I will leave it to Florian Meyer, who will discuss it on Friday, and also Felix Binder, who will also, I believe, discuss it on Friday. But the nice thing for us is that this gives us a bound which relates the achievable ground state population to the entropy production in this cooling protocol per step L. And why is this nice for us? Because here we are able to bound the fidelity we can achieve in terms of the entropy production we incurred to cool our resources down and improve the protocol, sort of coming full circle with what we wanted to achieve at the start. So to summarize, listen to Landauer. The free operations of your resource theory are not really free. And I feel obliged to say this to you guys. And now you can argue with me in the coffee break. Achieving better timekeeping means more entropy production or slower gates. Better timekeeping allows you to achieve circuits with higher gate complexity, and you can improve your states by cooling them at the cost of entropy production, and accurate quantum information processing comes at the cost of entropy production or irreversibility, as Julia told us. I'd like to thank my collaborators and thank you all for listening.
We have a time for a couple of questions. So, any questions for Jay?
I mean, the usual joke of either being too clear or too confusing.
I have one question, so there's no from the audience. How is that?
Thanks of timekeeping and fidelity in the computation. I seem to have seen in the theorem that you have to have independent clocks for each qubit, so to speak. That's not necessarily what is done in computation. Actually, you derive all the clock from one laser, let's say. How does that change it?
So I definitely agree with you, and indeed correlated ticks, like correlated clocks, and how they contribute to a computation has been something that we've been working on extensively for the past couple of months. And Florian has been wasting many of his fine hours on this very task. And so I suggest you can discuss it better with him. But I would say that this really makes the problem quite tougher because in some sense, it's only tractable in the IID setting. And you have to study how correlated ticks under reasonable assumptions still look IID. And this transition is quite mathematically interesting. And so all I can say is, keep your eyes peeled and hopefully it appears on the archive late January or something. But thank you for the question.
Excellent. I have a simple question. So you are assuming that your clock is important resource to bound your accuracy. So is there any kind of measurement is involved in doing your plot that measurement should be also included in your test of it? And sometimes you have to erase it. So is there this kind of consideration can come into your framework?
Yes, so you are definitely correct that measurement can contribute, and that's sort of why I wanted to examine this in the context of coding. But you are correct that in this picture, we do not consider the role of erasure in this step. And I would say maybe the reason why I wasn't motivated to do this was I felt that it was already dealt with in the literature extensively, like cooling qubits to the ground state, erasure, sort of. And again, that Felix will speak about this, and also Florian will speak about erasure in the context of computation. But you are definitely right that a full comprehensive picture of the thermodynamics of, let's say, quantum information processing has to take into account refreshing and how difficult this will be, how related to quantum error correction this is, and our ability to understand this, I think is definitely an open problem.
All right, so if there's no more questions, now I think it's time for coffee break. Yes, so let's thank the Jake again.